An AI can know a fact and still fail to say it. Worse, giving it relevant context can make that hidden fact harder to reach. 3 papers trace the same problem from diagnosis to training to a controlled intervention. Perhaps the bottleneck is access, not storage. The papers make 3 distinct moves. EchoQA verifies what a model knows, then shows context suppressing it. Ma and Hewitt use cues and answer-reward reinforcement learning to train better access. VAKE externalizes candidate facts as triples so their effect on a frozen answerer can be attributed. All 3 separate knowledge in parameters from information in the prompt. Parametric knowledge comes from training and lives in weights. Contextual knowledge arrives at inference through documents, retrieval, or structured triples. A correct answer may require either source or their integration. A wrong answer does not identify the failure. The fact may be absent, encoded but inaccessible, suppressed by context, recalled but misused, or lost during final answer generation. These mechanisms demand different interventions, yet ordinary benchmark accuracy collapses them into 1-0. EchoQA begins with the strongest behavioral control in the set. It asks each model a direct fact question and discards every item answered incorrectly. Only then does it add context and test again. The final test set is model-specific and contains facts that exact model just demonstrated. The benchmark then varies how context relates to memory. It can repeat the fact, supply a missing hop, contradict it, or be irrelevant. Complementary and irrelevant conditions are especially revealing. There is no principled reason for useful or harmless context to make a known fact less accessible. Yet complementary scientific context often lowers accuracy relative to no context. Llama 70B's unknown rate rises from 23.89 to 62. 72%, Quen's rises from 40.28 to 81.26. All required facts are written in the prompt, performance recovers, isolating the missing internal hop. Conflicting context is even more direct. Under neutral prompting, almost every model except O1 follows the prompt over verified memory in more than 90% of main conditions. A model can state a fact correctly one moment, then abandon it when a contradictory paragraph arrives. Relevant context also causes failure. On conflict QA, Quen chooses unknown 59% of the time, despite having answered the fact correctly before. The model is not simply deceived by a false claim, it is overconditioned on searching the supplied context. Prompting reveals that the knowledge has not vanished. Trust yourself helps, and forcing the model to state its own knowledge first can drive irrelevant context unknown rates below 5%. This is diagnostic evidence of latent access, but the paper calls these unnatural deployment prompts. A 200-example case study finds that in 93.5% of selected failures, Llama 70B relies on context and options, often declaring insufficiency. EchoQA's proposed mechanism is scheduling. Post-training may teach context-only and memory-only answer modes, but not when to merge them. That explanation remains speculative. EchoQA tells us to separate recall from reasoning before integration. The next paper asks whether reasoning models can be trained to perform that recall automatically, using no retrieval and no process labels, only whether the final closed-book answer is correct. The first experiment changes 4 words, think step by step. Cross-trivia QA and natural questions, 4 reasoning models gain 0.8 extracted recall points on average. Math is mostly flat or worse, suggesting factual access is under-optimized relative to domains already trained with reasoning rewards. The model first samples a reasoning trace, and then an answer conditioned on that trace. Forcing the trace empty makes the open model 6.9 points worse. Training opportunity is therefore not only which answer token is likely, but which sequence of internal associations gets sampled first. RLVR trains GPT open source 20B on Trivia Q, without supervising thought. Exact answers earn 1, reference containing answers 1/2, wrong answers 0, and malformed answer tags lose 1/10. Policy must discover whatever trace makes verifiable recall more likely. For each question, 8 trajectories compete against their group mean. Above-average attempts are reinforced and below-average attempts suppressed. This on-policy comparison matters because successful reasoning can evolve during training, instead of copying one frozen set of traces. Reasoning SFT is the decisive control. It collects 40,000 correct traces from the initial model and imitates them offline. That baseline improves recall modestly, but cannot generate better search strategies as the policy changes. Online RL can. The gains are large. TriviaQ exact match rises from 36.5 to 63. 6 natural questions from 6.0 to 18.2, and hotpot QA from 7.5 to 17.0. Training used only TriviaQA, so transfer supports a broader access policy rather than a single answer table. But better access is not automatically better explanation. Traces become modestly longer, yet corrected models often say the right fact earlier rather than reason more deeply. The answer reward cannot distinguish structured memory search from improved calibration or more accurate guessing. That ambiguity motivates the third paper. If activation remains buried inside freeform thought, improved accuracy cannot be attributed cleanly. VAKE first requires the policy to write candidate knowledge into an inspectable graph, then lets a separate frozen answerer reveal whether those facts actually enabled the answer. VAKE defines activation as a wrong-to-correct intervention. With question, sparse context, and frozen answerer fixed, the system fails. Add the policy's generated knowledge increment, and the same answerer succeeds. The increment is the only manipulated variable. Documents are converted to relational triples. Retrieval uses 2 graph hops, 5 edges per hop, removes triples containing the gold answer, and caps context at 10. The resulting subgraph supplies query-relevant cues while attempting to withhold a complete answer path. During priming, the trainable policy inserts bridging triples. A frozen answerer consumes the augmented graph and produces the scored answer. No gold triple labels are needed. The reward reaches the policy only through whether its explicit evidence helped another fixed model. During reasoning, the priming checkpoint answers directly from the original sparse graph. There is no insertion and no frozen answerer. This asks whether the learned ability to find the relevant fact transfers from an explicit experimental instrument into ordinary chain-of-thought behavior. Priming alone beats all non-reasoning baselines in distribution. Full VAKE reaches 33, 2 average on Quen 2, 5 and 34, 9 on Quen 3 with insertion and reasoning. Without test time triples, its direct reasoning checkpoints still lead, evidence that access training transfers beyond supplied facts. Across 6 model scales, more than 80% of inserted triples are judged non-derivable from the retrieved subgraph. On answer-bearing tail reproduction, VAKE-P reaches 35.2%, while frozen backbones through 72 billion stay at or below 27. This supports improved access to encoded associations. The evidential ladder is now clear. EchoQA shows a fact was behaviorally available before context suppressed it. Our LVR shows answer rewards can make that availability more reliable. VAKE shows explicit candidate facts can causally change a fixed answerer. Each closes a gap left by the previous paper, but none directly maps a fact to its neural storage location. Methods optimize different qualities. EchoQA has the cleanest knowledge possession filter, but synthetic context and model-specific test sets. Our LVR is simple and effective, but entangles access with freeform reasoning. VAKE improves observability, but depends on graph extraction, a frozen answerer, and LLM-based attribution judgments. The shared open problem is source-aware control. The model should know when to trust memory, when to trust retrieval, when to surface uncertainty, and how to show evidence without fabricating it. We still lack robust provenance, calibrated conflict resolution, faithful traces, and guarantees that generated bridge facts are true. These papers replace a vague statement that models know more than they show with a research program. Verify the fact before testing context. Reward access without pretending the trace is explained. Externalize candidate knowledge so its effect can be measured. The memory may be stored. Reliability depends on building the right path back.